Hello everyone, I hope you all are doing well. So in the previous session, I had covered the part 1 of this basics of CAE and FEA domain, that is CAE interview questions we can say. So I'm here with the part 2. Okay, I'll be covering a few basic steps here. Well, so I'm not the FEA or CAE expert. I'm just a learner who wanted to just go through the basics and try to just create the contents on the same for future generation. So if you feel like if you want to suggest us to add few more contents for the basics who wants to get into the CA domain, please do contact us and try to comment uh, just below this video which we are going to post it. Well, so let's get started with this today's topics, what exactly we need to deal with. Yeah, so the slide we had covered in the past session now. So I completely forgot to include one more important thing what exactly I needed to cover, that is this particular density. Okay, we're gonna add this one during the analysis, right? Young's modulus, Poisson's ratio, and the mass density for nonlinear material analysis. We're gonna include the stress strain curve, and for the fatigue analysis, it is stress versus number of cycles, isn't it? So why this mass density is added? So what is the importance of this? Actually, this question like someone has asked me during the one of interview which I had gone through. So I didn't know this answer of why we exactly had this mass density. So even we had seen in the past, like we had covered the Poisson's ratio, Young's modulus, stiffness matrix. So I didn't see this density which we are going to implement in the formulas and all, right? So the answer how I got it is like even I crossed it with multiple people and even I had connected to my colleagues and all, but the answers were quite okay, but exact answers even I didn't found with the researches which I had done for 10 to 15 days. Luckily, the same guy again conducted one more interview. So that time, finally, I asked the same question. So what exactly this density is? So why are we gonna take it? So he answered, so to check the mass of the specimen and whatever the model practically we are going to consider, that we need to validate, right, whether it is same or not. So we are going to just provide the boundary conditions and the material properties, whether at the final stage is it same, right? So to compare the mass, we're going to include the density into account. So this particular density value is not going to impact on whatever the results we are going to get, the stress and displacement and all. Okay, remember that. So in advanced analysis, as I explained before, so this is going to take place, but for now density is used to just evaluate the mass of the practical as well as the whatever the numerical model we are going to take, that one. Okay, I hope you got the clear-cut idea. Now one more question. So while we are dealing with the practical model and the CAD model, so how you gonna just evaluate these two? The answer is the mass. Okay, so we're gonna apply the material inside the CAD model. So we're gonna check the mass exactly how much it is, and the same thing we're gonna just weight outside as well. So we'll check the mass there. So if it is 100% accurate, we're gonna consider whatever the CAD model we have built it, that is 100% correct, right? So these two you need to remember. I hope it's clear. Okay, the next question is to deal with the element size. Element size in FEA, does it matter? Yes, it does. So how it is? So like the same question, no? Even during like while I was a beginner for the CA domain, I didn't know what exactly the size I need to apply. I simply used to add the Pino mesh and run the analysis, and what are the results I get? Go and submit. That I used to do. But when it comes to the results accuracy, there is no exact clear-cut formula to determine the best mesh to just deal with the every simulation. So to answer this, what exactly we do is, so we're gonna run the multiple analysis to deal with the results accuracy, that is mesh sensitivity we can say. So where we're gonna just simply run this model with several different mesh sizes, and we'll plot the results for the stress and displacement. Okay, there your mesh, whatever you're going to get, the size will be converged, where only the little amount of the variations with respect to stress and displacement you're gonna get it. So that time you can just consider whatever the results you're getting it. It is approximately nearly 90% or 85% accurate. Okay, to just consider the scenario into account, what exactly I have done is, so I had run the analysis considering the steel rod into account. Okay, and adding the hexagonal mesh. Okay, for different mesh size, and had evaluated the results for the same thing, and we'll see how exactly it gonna just give the variations. So properties you could see here, the radius and the beam length and the applied loading conditions and all, and the x modulus and all. So when it comes to the results, you could see at the right corner the mesh size I had considered 4 mm, 2 mm, 1 mm and 0.5 mm with respect to that element, and the nodes you could able to cross check. Okay, when it comes to the timing, for 4 mm it is took 0 seconds to solve, within just fraction of seconds you'll get it. For 2 mm 1 second, for 1 mm it is 5 seconds, for 0.5 took 70 seconds. So you can see the timing, right? So when it comes to the displacement, you could see only minute changes, only hardly 0.5 to 1% changes we can consider. Okay, 1%. When it comes to the 4 mm mesh, it is 5% to 6%. So when it comes to the stress values, could see it is 4%, and when it comes to the 0.5 it is 0%, and 1 mm mesh it is again 0%, right? Same thing I had presented here. You could see the analysis. So I had just simply showed you 0.5 mm meshing, and the maximum stress value is 213 megapascal. When it comes to displacement, it is 0.4 to 9. You could see the displacement graph. So for 4 mm it is approximately 0.45, and for 0.5 it is reducing. Same thing for principal stress, so it keeps on decreasing. When it comes to the time clock, you could see 4.5 to 70 seconds, right? So I hope you understood what exactly the variations is going on here. So I hope you understood, right, what exactly we need to consider, how we need to just evaluate. This is a simple process. So when it comes to the element type, the effect of element type on the mesh sensitivity. So here to deal with this answer, we'll take two different element types. One is the first order and the second order elements. So we call it as linear elements for first order, that is C3D4 simply considered. When it comes to the second order, we're going to consider the C3D10, so we can say it as quadratic elements. Okay, so we call it as higher order elements. Okay, so to deal with this, I had taken these two element types into account, and I had run the analysis, and you can just see the results here. So for 1 mm C3D4 and for 2 mm C3D10HS model, when it comes to the linear first order elements, the 5% error we have it. When it comes to the C3D10 hybrid, it is only 0.08%, right? So from this we can conclude that the second order elements gonna give us the better results when it compared to the linear elements, the first order elements. So now I'll take one more scenario. So this is the steel shaft, you could see. So I had considered the overall 0.5 mm mesh for entire model. I had meshed it, and when it comes to the second one, the adaptive model, only at the fillet regions I had refined it, and overall it is 3 mm mesh I had taken. So for this, once I run this analysis, you could see the results, the whatever the model is there, no, that is adaptive model, it is overall 80 times faster than whatever the fine mesh we have taken. The results variations you could able to see, no, not much. It is 154.9, 155 approximate. Adaptive model, it is same thing. When it comes to timing, you could see it is only 8 seconds, there it is 631 seconds. So 631 seconds. So 631 seconds. There it is 631 seconds. There it is 631 seconds. 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 631 seconds To conclude it, the selecting the right mesh sizes depends upon the what exactly the results accuracy you're looking for and the efficiency you're looking for. So the second order element gonna give you the more improved results, and actually the thing is it's gonna take more time as well as the computational cost. When it comes to hybrid meshing, which is very okay to follow the method, it is sufficiently accurate results for the uh, analysis. Okay, so finally it is all about you, what exactly results you're expecting and how accurate results you're looking for. So depending upon the requirement, we can able to consider it. So one more thing very important is the element types that I'm going to cover later. So we'll see one more thing, that is the plane stress and the plane strain. So what exactly these are, right? And which I need to consider while dealing with the analysis. Well, we'll cover this one in depth. Okay. So we already know we have the improved computers in this generation, right? So in short, this plane stress and plane strain we're going to consider to simplify the three-dimensional problems into two-dimensional slices in order to save the modeling, right, and the computational expenses as well. So it is very important. So to convert this 3D models into 2D slices, we use this plane stress and plane strain. Okay. Well, we'll see what exactly these and how exactly it's gonna help us. Yeah, when it comes to the plane strain, okay, this particular plane strain assumption can provide us the good representation of real components. So in this particular plane strain, we're gonna just neglect the z direction strains. So they're all set to 0. So this condition would exist in a in an object that is constrained in z direction by rigid walls. So this formulation will help us to completely avoid all the the shear stress and the shear strain, the plane strain values along z direction completely 0. Okay. Well, these assumptions are very good for thick components. Let's say we can take the dam into account. Okay, so where the loadings are considered along with only one plane, we can consider only xy plane. So the large amount of material through this particular thickness essentially renders through the thickness strain irrelevant. Okay, that whatever we're gonna consider, it is at least we can consider it as negligible. Okay, the diagram you can see, no, so no strain in the direction of z, so only the plane strain we're going to consider. Okay, when it comes to plane stress, okay, here what exactly happens is whatever the stresses you're going to consider, so along z direction, the stress along z direction are 0. Okay, so it is used to just analyze the very thin plates loaded with the same, like only in one plane, xy plane. But also it is applied to the surfaces of a thicker component as well. Okay, in a certain conditions. So what exactly happens here is, so we use stress along z which is equal to 0, and even the strain along z direction equals to 0. To simplify this, the formula you could see the calculation uh, epsilon, like the strain along zz direction, minus v inside the bracket the strain along xx plus strain along yy, where v is the Poisson's ratio. Okay, well, so to simply explain in a better manner, I'd like to add one more slide to just explain it in a short manner. You could see the slide, right? So what exactly the same thing here I had explained in a better manner. Okay, so here this plane strain is a state of strain in which the normal strain, okay, as well as the shear strain directed perpendicular to the plane of the body are zero. Okay, we're gonna just consider only the xy plane loading conditions along with the z, the loading conditions like the normal strain and the shear strain. Remember the strain, okay, are zero, completely zero. Okay, so this assumption is used for the long bodies in normal direction with the constant cross section subjected to the loading acting only in the xy plane. Very important. Example is a dam, as I said before. So when it comes to the same thing, that is plane stress. So this is the state of stress in which the normal stress as well as the shear stress perpendicular to the plane are zero. Okay, so you could see the diagram here. Okay, so it is mainly used for the thinner membranes. Okay, uh, the loading conditions only along xy plane can be considered under this particular plane stress. Okay, to summarize this, I'd like to add these points. Okay, so if you want to choose plane stress to simulate the interior of the very thick component loaded in a single plane, so you can see the image there. So if you are considering the dam into account, we're gonna just consider the strain along z direction. It is completely zero. Okay, we're gonna choose the plane stress to simulate the very thin components when it is loaded in plane only. Okay, you can see the plane stress here. The stresses along z directions are zero. Okay, okay, this is the short explanation about the plane stress and the plane strain. And simple, we're gonna just consider the 3D elements and the 3D models. We're gonna just convert them into the 2D models to just save the time as well as the computational expenses to get the more accurate results. Okay, so this is what exactly the explanation behind this plane stress and the plane strain. I hope you got it. Yeah, so as I said before, I wanted to just explain more about this element types. So which element type should finite element analysis simulation use, right? So if I consider Abaqus, so there are different types of elements with respect to the family, degrees of freedom, number of nodes, formulations and integration. Okay, when it comes to the element family, you could see the image below. So there are some solid elements, shell elements, okay, beam elements, truss elements, the rigid elements, okay, the continuum for solid as well as fluid elements, okay, which comes under the families. So depending upon these again family, we're gonna have again element types, so that I'm going to explain later. Okay, so this you need to remember. Depending upon the what family we are looking for, what type of analysis we are considering, we're gonna consider these things. Yeah. So now Abaqus element types. So the degrees of freedom define the variable being calculated during this analysis. So and fundamentally control the elements behavior. So how exactly this degrees of freedom gonna implement on this elements, we'll see. So for example, if we consider the solid elements possesses only active translation degrees of freedom, okay, the solid elements. When it comes to the shell elements, this is going to have the translation as well as the rotational degrees of freedoms. Okay, very important term. For the stress and displacement analysis, we consider these two. For the temperature distribution and the acoustic pressure and all, so we're gonna have the different element types that we'll discuss later on. Okay, so now what we can consider here is, so let's say if we consider the 3-noded triangular versus 4-noded quadrilateral elements. Okay, when they deform, the 3-noded triangular results in the state of constant strain. Okay, and therefore less complaint than the 4-noded quadrilateral elements. So additionally, the number of nodes and the elements what we are going to consider, it has dictates the strategy that will be used to interpolate the degrees of freedom calculated at the nodes to rest of elements. Okay, in Abaqus, we have, there are two available orders. One is the first order and the second order, right? Even in SolidWorks and other softwares and all, we're gonna consider these two orders. One is the first order, we call it as linear. Second one is second order, that is quadratic. So you could see the nodes here, right? In the first order, we're gonna have the elements only at the corners. When it comes to second order, the elements have the corner nodes as well as the mid-side nodes. You can see we have taken this solid brick model into account, 8 node, that is C3D8. When it comes to this 20 node quadrilateral element, which has the second order properties, that is C3D20, we can consider. Fine. So with respect to the requirement, again we have refined these Abaqus elements. When it comes to the distinct element type, there are two element types. One is the Lagrangian and the Eulerian. So very important. So for the static analysis and stress and displacement analysis, what we're going to consider, Lagrangian or Eulerian? So we're going to consider the Lagrangian model to describe the elements which deform with the material. So when it comes to Eulerian elements, they are fixed in a space and flow, allow to material flow through them. Okay, so in short, to deal with the stress and displacement analysis, we take the Lagrangian elements into account. Okay, so the Eulerian elements are more suitable for the fluid flow analysis like CFD and all. Well, inside we have these subdomains that we're gonna just discuss later on. Again, these what examples we are going to consider, they have been again refined in the form of hybrid, again the incompatible modes and the modified formulations exist. Okay, even reduced modules and all, so that we'll see later. Again, with respect to the requirement, like the shell elements, we have the thin and thick elements, okay, for the plane stress and plane strain considerations and all. Fine. Yeah, so this is the brief explanation about the elements. So for the general 2D solids, we're gonna consider these C3D4. It is linear first order elements we can consider, and C3D6. In short, it has the 6 nodes. Again, it is the linear triangular prism element. When it comes to C3D8, you could see it has the 8 elements. So when it comes to the C3D8R, it is reduced integration. So what exactly it is, we'll see. So again we have the C3D10, 15, 20. Again C3D20R, that is reduced integration. And again when it comes to this C3D20RI, that is the incompressible C3D20 with reduced integration. Again when it comes to the heat transfer, we have this DC3D4. It is identical to the above modules, okay, the elements. When it comes to shell elements, we have the S6, S8 and reduced S8 integrated. Okay, when it comes to plane stress, we're gonna have this CPS6 and CPS8 and CPS8 reduced integration. Even for plane strain, we have it CPE6 CPE8. We'll see in the next slide. So now what exactly this reduced integration? So Abaqus uses integration to determine the various quantities throughout the volume of the element. Okay, the material response is evaluated at each integration points. Okay, which exactly going to consider the Gaussian quadrature, because each integration point requires the mathematical solutions, right? So it logically follows the elements with more integration points computationally more expensive as well, and gonna consider more time, isn't it? So to that end, the several Abaqus element families provides the reduced integration option, where we can just take the fewer integration points than the standard whatever the element formulation we are going to consider. When it is appropriately reduced, integration elements can substantially improve the model efficiency as well as the solver timing runtime. Okay, so again you need to take care of this particular reduced integration elements. Why? Because they have some limitations. So if you want to use them, so consider with respect to the requirement, or else they might lead to inaccurate results. Yeah, so now we have the elements for plane strain. As I said, it is CPE6 and CPE8, and CPE8 are reduced integration. When it comes to other, we could able to see for beam we have the B32 and B32R, and special elements like D3 and this all. So when it comes to this S8, S8R and CPS8, and even we can consider B32 and B32R elements are the internally expanded into the 20 nodes. Okay, for brick elements. Just remember these all the elements. Right now, if you are the beginner, if you want to get into the CAE domain, you don't need to worry about these all the things. So just we're gonna deal with the few analysis. So with respect to that, we will be just having the default set of the element types. We can simply take them and we can start working on. So this is overall just explanation about why we're gonna consider the mesh uh, accuracy as well as the element types. Okay, so what exactly the plane stress and the plane strain, okay, how we gonna just include these things. So this is a few things I wanted to just share you guys. So I hope you got the better idea about what exactly these things are. Okay, yep, so that's all about this session. So I hope you got the basic idea how we need to consider the mesh, and what type of element we need to consider, and what type of approach we need to follow to get the more accuracy with respect to the results. Okay, what exactly the plane stress and plane strain are when we need to consider. Okay, and what exactly the different types of elements are there with respect to the requirement. Okay, 1D elements, 2D elements, first order elements, second order elements, what exactly they are, and 3D elements. Okay, when it comes to Abaqus and other solvers, how they have differentiated, and which kind of elements we need to use. Okay, well, so that's all about this session. So later on I'm going to cover a few more things with respect to basics of CAE. So as I said earlier, if you are just new to this particular CAE domain, we want to get into the CAE domain, so we are trying to just recall all the basics needed to get into these things. So people who are expertised in this all the CA domain, if they feel like the content needs to be refined, if they want us to add few more things inside, or if they have any suggestions, please do reach us. So we already given the number. Please do comment if you like the contents, or if you want few things to be added, please do suggest us what exactly things we need to include in these series of CA basics tutorials. Well, thank you guys. Stay tuned. Bye everyone.